Hello, my name is Patricia Suzanne Eastwood, and today I will be discussing Lab 5. So the goals of this experiment were to collect data on a magnet falling inside a tinfoil tube representing an induced magnetic field, and to model this observation computationally and compare the results. So the checkpoints were that you could not use ferromagnetic material because of how the magnet would change the layout of the domains within the material. So as an example, for something like iron, if you put a coil underneath it, it would definitely change the domains and cause it to have a very different change and perhaps even a permanent magnetic dipole. So the magnet falls at a slower speed due to its attraction to the aluminum tube. And a magnet falling at free space would fall at an acceleration of 9.8 meters per second squared due to gravity as the only contributing force. So the concepts were kind of forces on a magnetic dipole. So we know from our prior labs that a bar magnet is a magnetic dipole. So ultimately, our goal is to be able to determine how this is affected. So we actually know that the magnet creates an induced current, which can be calculated by dividing the tube into rings, a distance y from the radius. This current creates a magnetic field to counteract gravity. So what we're going to see is that a repulsion is going to occur, which is why the magnet is going to fall at a different speed than it normally would. So we are given the EMF, we have the resistivity, and we have the circumference of the tube. So from this, we're able to calculate the current, and from that plug it in to find these individual forces acting on the magnet. So we have current times the length and the cross product of magnetic field equals this change in force. So the conditions that we have are a 1 centimeter thick of aluminum, an inner radius of 0.031 meters, and a length of 0.31 meters. And we repeated the experiment 5 times to get a time in which the magnet fell and entered the tube and left. So the average time for this to happen is 1.82 seconds. And I also demonstrated this in a video. So that was a very quick video, but that's kind of what was happening. So now we wanted to simulate this with our code. So we wanted to see how these forces calculated with the rings would interact with the system. And we used our mu from a prior lab. And we really needed to update our positions, velocity, and force. So I'm going to go into my code and kind of walk everyone through this. So our conditions, as shown in a previous slide, are kind of given here. We also need to include the width and the inner radius for the total radius. So a lot of this was given to us, but we wanted to be able to calculate the change in flux over time due to the falling magnet. From that, we needed to know when it entered and exited, and we wanted to be able to simulate this. So kind of the main parts that are very important here is that the things that are going to be updated is the net force, because it is it's changed by both gravitational force and magnetic force. And then also this net force is then plugged in to find the updated velocity, and then the updated positions. So since we know that F net equals mass times acceleration, and then mass divided by mass would be 1, so acceleration times change in time is going to equal velocity. And then finally, we know that position is going to be, since if we even look at this in units, velocity is meters per second. If you multiply that by seconds, then you get meters, which is the units for position. So then we want to be able to plot this in a velocity time graph, and if we run it, this is demonstrated to us. So ours is very similar to the results that were shown in our observations. Here's a demonstration of how the magnet will fall out, because here the current is being shown. This zeroes out because, as you know from Physics 1, it's going to eventually reach 9.8 meters per second squared. Eventually, the goal is for the velocity to zero out. So we were right in this regard. So if we go back, our additional questions are: what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So this would cause the current to increase, thereby causing the magnet to fall at a slower rate. This is because more repulsion occurs when the current is increased. And we know this from the formula that force equals current times length, cross product magnetic field, because a greater current equals a greater force on the magnet. So then what if the holes or slots were cut into the tube? How would this affect the ring currents in your model? So we know, going back to that formula, that this will cause the tube's dimensions to decrease. This causes less of a force, so less repulsion occurs. So the magnet would fall at a faster rate. Therefore, the ring currents would actually increase, and it would be to counteract this, so that the magnet would still reach terminal speed, kind of as demonstrated in that graph, because eventually it does have to reach that. So, in conclusion, the induced current did cause the magnet to fall at a slower speed, and a repulsive force occurred against this magnet. Thank you so much. I really hope you enjoyed my presentation.